What's up guys, welcome back to Dynamic Programming for Beginners. This is part 17 and today we're going to use dynamic programming to solve a graph problem. Specifically, we're going to try to find the shortest path in DAG. And what is DAG? Well, DAG stands for Directed Acyclic Graph. If you are not familiar with graphs, I strongly encourage you to go and read about it online. Graphs is an important topic. It's a large topic. There are a lot of real-world problems that can be modeled with graph theory, so every programmer should know about graphs. Today we're going to briefly talk about the basics, which is obviously not everything. So please make sure to spend some time and become familiar with graph theory. Okay? So what is a graph? A graph is basically a set of objects known as nodes that are connected by links known as edges. Let's take a look at some denotions here. So we can denote a graph as a capital G, and a graph consists of, as we've just said, consists of nodes or vertices denoted as V and edges denoted as capital E. Let's take a look at some examples of basic graphs. So here is an example of an empty graph. This graph does not have any nodes and it does not have any edges. Here is another example of a graph with just one node named A. Let's take a look at one more example. Let's say a graph with two nodes, A and B. There is just one edge between them. Here is one more. A, B, can be like so, C, and then maybe D. Right? So this graph has four nodes and three edges. We can even add another node here, E, over here, and this can be, one graph, but E is on its own. But it's still part of the graph, okay? Now, what about directed acyclic graphs? So if we look at this specific graph over here, we can notice that there are no directions between our nodes, right? And there are many problems where direction actually exists, right? So for instance, if we were to model maybe cities and roads between those cities, there is a direction that you can go like from one city to another, right? So for instance, if I have nodes being cities, so for instance, this is New York, this is, let's say, San Francisco, LA, maybe from LA you can go to Washington, D.C., and then you can potentially go from San Francisco to D.C. as well, right? So we can go from New York to San Francisco. We can also go from San Francisco to LA. We can go from San Francisco to D.C. And maybe you can go from D.C. to LA. But you are not allowed, like according to this specific graph, you are not allowed to go from San Francisco to New York. You are not allowed to go from DC to San Francisco. So from DC, you can only go to LA. From San Francisco, you can go to DC and to LA. Okay? So this is what directed graph means. Now, what is acyclic graph? Acyclic graph means that there are no cycles in it. There are no loops. So this current graph does not have any cycles. But if I were to draw one more edge, for instance, from San Francisco to New York, then there is a cycle. Because we can go from New York to San Francisco, and then we can go through another edge back to New York. And this is a cycle. We're not going to consider this type of graphs today. We're only going to talk about directed acyclic graphs. So edges have direction, but there are no cycles, okay? What else can we say about graphs? Well, another thing is that many problems have certain entities, like in this example, we have cities like New York, San Francisco, LA, DC, right? But there are no any values, and many problems actually have some values, right? So for instance, you may want to find, like in the problem that we are going to consider today, we're going to find the shortest path. And if we're looking for a shortest path, we have to define what a path is, right? So for instance, a path could be the time between cities. So if I want to get from New York to DC with the shortest time, well, this is not the best example, maybe from New York to LA, right? So let's say from New York to San Francisco, it could take like 4 hours. From San Francisco to LA is, let's say, 2 hours. Then from New York to San Francisco, from San Francisco to DC, let's say it takes 2 hours, which is, I know it's weird, but just for the sake of example. And then from DC to LA, let's say it's 1 hour, right? So in this specific example, you can see that to get from New York to LA takes 6 hours, right? 4 plus 2. And then to get from New York to LA through DC takes, what is it? It's 4 plus 2 plus 1, it's 7 hours, right? So it makes more sense to go through San Francisco in this specific case, right? So this is known as weight and denoted as omega. And weight can represent pretty much anything. It depends on your problem. It can be time, it can be distance, it can be whatever, it can be anything. So it depends, it entirely depends on a problem. All right, so here is a sample graph, A, B, C, D, E, F, right? So we have, what is it? 6 nodes and a bunch of edges, right? As you can see, all the edges, as we've said, the graph is directed. So we have directions from each node, right? And we also have weights. We do not have any cycles, so you can only go from, you cannot go back essentially as soon as you leave any node, okay? Now, what's the goal here? So the goal here is to find the shortest path from A to F, okay? So how are we going to solve this problem? Well, we have a framework, right? We usually, first we try to define the objective function, then we specify base cases, then we assume that the problem is already solved and stuff like that. And usually the process is that the sort of like the framework that we follow and its process looks like this. So we have some function n, right? We assume that the problem is already solved. Then by knowing this value, we solve f of n minus 1. Then we solve f of n minus 2. And eventually we solve f of 0, which ends up being the solution to the entire problem. So we first solve this guy, then we solve that guy. Knowing f of n minus 1, we solve n minus 2, and eventually we solve the entire problem, right? But how can we apply this rule here? Like, there is no specific order. Like in here we have some order, right? But over here, when we're looking at a graph, there is no order. Like, okay, we can find the shortest path here potentially, right? But then what are we going to do? Are we going to look for a shortest path from D or from E? Like, what are we going to do here? There is some sort of like a chaos here, right? And there is no order. And this is why I decided to pick this problem, because there is some sort of like a trick or like a thing that you have to do before you can apply dynamic programming. And this is the thing that I would like you to learn about today, okay? So when you're trying to solve a problem that does not have a specific order, then you have to create that order, okay? And in graph problems, in this specific problem, when it comes to directed acyclic graphs, there is a specific property that we can leverage. And that property is known, there is a certain like protocol that we can follow in order to actually create an order for any directed acyclic graph. And in this specific problem, for instance, we can use something known as topological sorting, right? Top sort for short, top sort. And if we apply topological sorting, then this graph will have its own order. And what is topological sorting? Well, it means that all the nodes and all the edges go to the right. All the arrows of edges go to the right. So let me actually show it to you because it's a little bit hard for me to explain in English. So in this specific case, we have A, right? Then from A, you can go to C. From C, you can go to B. From B, you can go to D, or you can go to E, right? So we can say you can go to, let's say, E. I think that's the right way here. And then from E, you can go to D, and then finally we can go to F, right? Now, let's outline our edges. So from A, I can go to B and C. So I can go to B, and I can go to C. From C, I can go to B. I can also go to D. And I can also go to E. Right? Now, from B, I can go to D. I can go to E. And I can go to, from B, I can go to D, I can go to E, and that's it. Now, from E, I can go to D, and that is it. And from D, I can go, from E, I can also go to F. And then from D, I can go to F. So this is a topologically sorted representation of this graph. As you can see, all the edges go to the right, right? They always go to the right. And that means I can literally use a, like a for loop to go through this, through these nodes. And now there is an order. Now we can actually go to the second step and apply dynamic programming. The implementation of top sort is not something we're going to consider today. It's outside of the scope of this course, right? This is something you can take a look online. For this problem, we will assume that the graph is already topologically sorted, okay? But we can actually now apply dynamic programming, right? We can say that we can find the shortest path for this guy first. Then we can find the shortest path for this guy. Then we can find the shortest path from here. We can find the shortest path from B, shortest path from C, and then we will find the shortest path from A, okay? So let's follow our framework and solve this problem. So the first thing that we usually do is to define the objective function, right? And in this problem, the objective function is pretty simple. It's already kind of like in the description. So f of I is the shortest path from I. That's pretty much it, right? So we can say that if we are standing here at F, what's the shortest path to get from F to F? So it's F of n. It's 0. We don't have to, it doesn't cost us anything, right? Now, let's say we're standing here at B, right? So when we're standing at B, it's F of, well, we can say that this is 0, 1, 2, 3, 4, and 5, right? So we have 6 nodes. So B is the second node, F of 2 equals. So what we can do here, we can go from B, we have 2 options. And we always need, so this one doesn't have a weight, so let's say the weight is 3. From B, we can go to D, or we can go to E, right? But we need to pick the minimum, right? Because we're looking for the shortest path. So we say, when we are at B, when we are here, or here, we can go to E or to D. So we need to pick minimum. So it's a minimum between. If we go to D, we have to pay weight from going. So let's say this is I, right? And let's say this is I, because we said that F of I is the shortest path from I. So we're looking for shortest path from B to F, right? So if we go to D, then we have to pay omega of ij, right? And this is going to be 5. But then we will arrive here, and it's not f yet, right? So it's j. So we will have to pay, we'll still have to pay f of j, right? And that's pretty much it. This is our formula. Well, this is f of I, not f of 2. So if we were to solve for f of 2, it would be f of 2 equals minimum between, so we would have to pay 5 plus f of 4, or minimum between, if we go to 3, if we go to E, we have to pay 3, and we still haven't reached f, so we go f3 plus f of 3. So by doing all of that again and again, we will eventually get to here, which it would be f of 0, and this would contain answer to the entire problem. Let's code it up now and see how that works. All right, so let's write some code. Here is the problem. Given a graph as an adjacency matrix, find the shortest path from the first to the last vertex. So here is the function definition. We're given a graph. I've got a test here. As you can see, graph is defined as an adjacency matrix, meaning it's a two-dimensional array where rows are out nodes and columns are in nodes. Let's take a look at a visual representation of a graph that we are working with. So this is how the graph looks like. As you can see, I highlighted the best path, the shortest path. It's 0, 1, 1, 6, 6, 7, 7, 9. And the cost of this path is essentially 7, right? 4 plus 1 plus 1 plus 1. So when we work with adjacency matrix, it's super simple to get a weight of a specific edge. So for instance, if I want to know what's the weight from 5 to 7, I can simply call graph of 5 to 7, and as you can see over here, graph of 5 to 7 is 3, which is defined here, 3. Cool. So now let's write the code for our function. So the first thing that I'm going to do is to check whether a graph is even given to us. So if it's not given, we'll simply return 0. Now we can say, what's the length of a graph? It is n. We'll preserve it in n. Now we want to define our DP array, which is what we are going to use as a storage for subproblems, and this DP array is of size n. Next, I'm going to, let's actually write the objective function and all that stuff. So the objective function in this problem, as we've said, objective function is f of I is the shortest path from I to the last vertex, right? Now, what's the transition function? Transition function. So we are going from I to j, right? So f of I equals minimum the weight that we have to pay going from I to j plus f of j. The reason why f of j is because when we get to a certain point, so like for instance, if we go from 2 to 5, this is I, this is j. So when we go from 2 to 5, 5 is not necessarily the final destination, right? So we still have to go from 5 to somewhere else, right? So this is f of j. All right, what's the base case? So the base case is f of n equals to 0, right? Because when we are standing here, we don't have to pay anything to get here. Like if we are given one node, there is no path there essentially. So now, so having said that, we have our DP array. Let's also initialize it to infinity, or not infinity really, it's math max int 64 because Go doesn't have infinity. Let's define the base case, dp of n. Well, I'm going to use n minus 1 because n is the total length, and to access the last element of this array, it's n minus 1. So dp of n minus 1 equals to 0. And now we can start traversing the graph. So we already know the solution to the last subproblem, right? N minus 1. So we can start traversing the array from n minus 2, and then all the way down to 0, and then I minus minus, since we are going from high values to low values. And now we can start looking at each edge that is going out from node I, starting from 0 all the way up to graph of I, j plus plus. Now, if there is some weight, so weight is essentially graph of ij, right? And if weight is positive, then we can apply the transition function. We can say dp of I equals, this is the transition function. We say minimum between what we currently have and weight plus dp of j. And that's pretty much it. Let's return dp of 0, which is where the final result should reside. Now I think we can run our tests and see if things are working correctly. Okay, so everything is good. The 7 is what we wanted, and the test has passed. So I hope this video makes sense to you guys. Please read about graphs. Graphs are amazing. They're important. Graphs are everywhere. A ton of different real-world problems can be modeled with graphs. So graphs are cool. Please read about graphs. We may potentially learn more about graphs in the future and do more problems. We'll see. But that's it for today. Thank you so much, and I'll see you soon. Bye.